Okay, so I hope this slide is visible in PPT mode.
Yes, ma'am, it is.
Okay, okay. So good morning to all, and uh, in today's class we will discuss the condenser, design of condenser, which we have started from the last class. And in the last class we have completed Bell's method, and I have given two problems to you to solve, and the that what we can say, that problem we will discuss in Sunday class, where I expect the solution from you, and I will just check the values and will let you know if something will go wrong in your calculation and all. So like that. But before coming to Sunday class, before joining Sunday class, please solve both the problems. Okay, so that is your assignment to you, or we can say just exercise for you. In the last class we have started design of condensers, and in that we have first we have first saw that what is a condenser and what are the uses of a condenser. So that we have seen in distillation column, power generation cycle, and refrigeration cycle. Okay, so these are some primarily use of primary use of the condenser, and we can use other way also, because it is used to condense the steam or condense the vapor. So wherever it is required we can, and as far as this design is concerned, we can consider design of shell and tube condensers only. And because here phenomena is different means one side, if I consider the coolant side, there I am having the sensible heat transfer, but other side where I am having vapor or steam, there we expect the phase change or latent heat transfer. Okay, so in both way the phenomena is different, and therefore the shell and tube heat exchanger, which I am considering over here as condenser, it will have some change. Okay, so the first change is the baffle spacing. If I am considering condensation in shell side, the baffle spacing should be equal to shell dia. Okay, and otherwise it is like similar where I'm having condensation in tube side. So shell side we have normal sensible heat transfer. So we have normal consideration as we have discussed in shell and tube heat exchangers. Okay, so that is one thing. And next we have discussed the types of condensers in the category of shell and tube. So that we have categorized based on orientation as well as based on condensation site. Okay, so if condensation is occurring in shell side or tube side, that we have seen, and orientation horizontal and vertical. Okay, so the thing how to choose the correct condenser, because the design will depend on that type of condenser. It's not uniform. Okay, as we have discussed in shell and tube heat exchanger, here phenomena is different, so we have to consider the design differently. Okay, what that difference is and how to consider that, all that we will discuss in today's class. So when we consider that orientation, when we need to choose the horizontal orientation or vertical, it will depend on the heat duty. If heat duty is large, we need to go for the horizontal condensers. Okay, horizontal orientation. Okay, and shell side and tube side condensation, if your vapor is corrosive in nature, then only you will choose a tube side condensation. Otherwise that would be condensation will always be preferred in shell side, because coolant is in most of the cases it is water and it has more fouling tendency than the vapor. So in that case we will allow water to tube side, and if corrosive vapor you are dealing with, then it should be allocated to tube side, otherwise always shell side. So I have already told you the guideline how to choose the orientation and the condensation site, and accordingly you should proceed for the design. Now if I consider this uh, different type of condenser of shell and tube type, firstly we have horizontal shell side condenser, and we have discussed its the that we have discussed a few points about this, and the major point is like along with the shells along with baffle spacing, the baffle cut should be vertical, not horizontal. Okay, if I'm considering shell side condensation. Okay, so baffle cut should be vertical because we prefer side to side movement of the vapor instead of sinusoidal. Okay, so that you need to consider, and apart from that we used to have E type shell, and uh, we used to have like uh, notch, okay, baffle with vertical cut and V notch at the bottom, so that condensate can be released easily. Okay, and next, whenever I'm considering the vapor or steam, whatever the purpose is, in that equipment we consider two additional accessories, and that is vent, as you can see over here, just opposite side uh, where the vapor or steam is entering, we used to place vent, and secondly the condensate to exit at that place, we used to consider steam trap. Okay, that you must have heard before. Okay, probably in heat transfer course or like that. So in that way we consider horizontal shell side condenser. So from now onward I am not going to discuss about vent and steam trap. You know that wherever I am having the vapor, these two accessory will remain there always. Okay, so that is horizontal shell side condenser. Next condenser I am having is horizontal tube side condenser. Okay, so horizontal tube side means vapor will enter in tube side, horizontal placement, and you see vent is available just opposite side to this, and condensate wherever it is exiting, we need to put the steam trap, right, to avoid the steam to waste. And obviously shell side I am having the coolant, so that is inlet and outlet, and then in that case baffle will be normal. Okay, because movement of will be like this. Okay, not side to side by side. Okay, in that case from side you will see these line to be covered till here. Okay, this baffle line should cover till here. Okay, but here we don't consider body, vertical what we can say cut in the baffle, it should be horizontal cut. Okay, so when I'm using this type of condenser, okay, that I have already discussed, and you can tell it that whenever you are dealing with corrosive vapor, only at that time we need to go for the tube side condensation. Okay, second point is very important, that is high pressure. If your vapor is available at high pressure, okay, then in that case you need to consider the tube side condensation, because high pressure tubes are cheaper in comparison to high pressure shell. Okay, so these two conditions you need to consider in mind, and then you can choose. Okay, so this is horizontal tube side condenser. Next I'm having is vertical shell side condenser, and vertical shell side condenser, when I'm considering, the orientation is vertical, as you can see over here. Shell side condenser, we have to enter we have to let vapor enter to shell side. Okay, so vapors enter at top of the shell and flows down because it is vertical, um, along with the condensate which is removed at the bottom. Okay, so when I ask you that what is the usual movement of vapor or steam, okay, you can tell that you understand that the movement, the natural movement of the vapor or the steam is upward because of the density. Okay, but here we consider we enter the vapor from the top, which flows down. Okay, um, and condensate will exit from the bottom. In that case, I'm not allowing vapor to enter from the bottom and move upward, which is the usual pattern for vapor to move. Okay, the reason being that when vapor is entering from the bottom, and whenever condensate proceed, okay, when condensation proceeds, the condensate will be collected at the bottom always, right? Because of the gravity, it will come down, which will pose, or which will create hindrance in the movement of vapor from the bottom, because it has to pass the complete what we can say, the complete liquid which is available at the bottom, which is accumulated at the bottom in the condensate form, because anyway it will exit, but that exit will not be very sudden, that will be very slow. Okay, so in that case, vapor entry will be different in difficult when it is entering from the bottom. Therefore, vapor enters from at the top, okay, and then condensate proceeds, and because at that, when we are letting vapor enter from the top, it will not go upward, obviously, because root is at the towards end. Okay, so it will flow, it flows down with the condensate, and then we can have the complete what we can say, the tube available for condensation to proceed. Okay, in that case, vent is placed near the bottom of the shell, but of course above the condensate level. Okay, if you see, this is the condenser where vapor enters from the top. Okay, and in that case, the baffle cut would be usual, like from this side only it has the cut. Okay, not the vertical cut. Okay, so in that way we can consider this vapor inlet, and as the sorry as the condensate proceeds, that it brings the vapor to move down, and condensate exits from here, and above that we usually place the vent. Okay, and steam trap will be placed over here. Okay, coolant which enters into tube side, that you can see. Okay, and then exit of the coolant will appear over here. Okay, so in that case, in that way you can consider shell side condenser placed vertically. Okay, so this is the uh, another type of condenser. Now we have vertical tube side condenser. Okay, vertical tube side condenser, when I am considering, so vapor enters here, also vapor enters from the top and moves down. Vapor will never enter from the bottom. Okay, so in that case, vapor enters from the bottom, from the top, and moves down. Okay, so it includes E type shell, as we have discussed before also. It is E type shell, and coolant enters from the bottom and moves upward. Okay, from here it will exit. Okay, are you getting any sound of that uh, some sound is coming in between? Is it disturbing, like this, some sound of hammer, because construction is going on just beside room? Is it disturbing?
Yes, the sound is coming, but not much.
Okay, so whenever it will create disturbance, please let me know. I have already told them to stop, but in between maybe something is required. Okay, so please tell me, though I am already asking them to stop. Just wait. I have already told them. Just 1 minute. समीक्षा भाई इधर आइए. Okay. So thank you. So I have asked them to uh, keep it low sound, but please tell me if it is getting more disturbing. So here actually vertical tube side condenser and vapor enters from the top, and it proceeds down along with the condensate. And if you see here, I'm having a little bit different assembly. If you consider this side as well as this side, okay, and it is only in the vertical tube side condenser, not other condenser, as you can see before. Okay, if you consider this side and this side, more or less that covers size is cover height is same. Okay. Okay, so here also if you see, this is cover side and this cover side, it is almost same. Okay, but it is more in the case of uh, this vertical tube side condenser. Okay, and if you see at the bottom we have different assembly. One is of this funnel type. Okay, and the reason being because condensate will coming from tube side, right? So instead of because if you imagine the condensate, how it will come, it will not be very runny. Okay, like drop wise it will come. Okay, as the condensate proceeds, it will be converted into drops, and that will come. Okay, so if this type of assembly will be kept, it is only for smooth removal of the condensate. As you can see here, this type of baffle we used to place, so whatever condensate is coming, it will get directed to this exit. Okay, so in that way, this section is of more height in comparison to this section. Okay, or in you can see like this. Okay, so this is the only difference in geometry for vertical tube side condenser. Otherwise the design of this would be same as we have design of other condensers. Okay, so that is about all type of shell and tube condensers, and we will proceed towards design of condenser. And here I am having this uh, uh, condenser, some fundamentals of the about this condensation. So when I that you must have learned in your heat transfer course, that when we go for the condensation, usually we have two type of condensation. First is the film wise condensation and second is drop wise condensation. Okay, so whenever I am considering this film wise condensation, it is usually made for the smooth surfaces. Okay, and when I'm considering this drop wise condensation, drop wise condensation, when it is there, I think uh, I think drop wise condensation will be for smooth surfaces, and that shell, what we can say, the film wise condensation will be for like a little bit rough surface. Okay, because in drop in a smooth surface, the the whatever drops are there, or whatever condensate will be there, it will instead of accumulating, it will be distributed in terms of drops. Okay, if film making of film is difficult over there. However, that would be easier when I'm having little bit rough surface, because all the condensate will join each other. Okay, in that way, what we can say, that drop wise condensation when I'm having, because regular film is not there, and that regular film works as a resistance. Okay, it will create resistance in pass what we can say, for movement of the heat. Okay, therefore the when we compare the heat transfer coefficient would be higher for drop wise condensation, because it has drops, and it will create less resistance in comparison to film. Okay, because film of definite thickness, if it is there, it will create more resistance. Okay, it will work as a blanket, that you can understand. Okay, so that will not be much in drop wise, and therefore heat transfer coefficient would be higher in drop wise condensation. However, when we consider the expression which are available to predict the heat transfer coefficient, that are what we can say, that are more that prediction would be easier for film wise. Okay, and the equation or the empirical correlation for heat transfer coefficient, whatever has been developed, that is specifically for film wise. So though heat transfer coefficient in film wise would be lesser, we will consider the same expression to calculate the to design the condensers, not drop wise. Okay, I hope it is clear to you. So film wise condensation we will consider to design the condenser. Okay, now we will proceed for design of condenser, and as it is the as it is shell and tube type only, the design procedure will remain same. Okay, design procedure means whatever steps I am having, those steps will remain same. Okay, like we need to find out the heat duty and properties and all, so all that will remain same. Where I'm finding the difference will be found where I'm considering heat transfer coefficient, because heat transfer phenomena is different over here. Okay, so when I'm considering tube side or shell side, wherever I'm having sensible heat transfer, okay, the procedure will remain same as we did previously for that shell and tube heat exchanger. Okay, however, wherever I'm having the condensation, there that side heat transfer coefficient prediction would be different. Only that much change you could have, otherwise procedure will remain same. So I'm not going to discuss the detailed procedure. I'm only going to cover wherever you will find the change. Okay, so first of all we need to consider the physical property, because sensible heat transfer, wherever it will be there, the collection of physical property would be at average temperature. There is no difference. Okay, as we considered before, okay, for shell and tube heat exchanger. However, whenever I am having the condensation, that site, the physical property collection would be at different temperature. How? Like physical property of condensate for use in the following equation, which we are going to discuss, that will be evaluated at average condensate temperature. Okay, when you can have the condensation, that is phase change phenomena. Phase change phenomena also, of course, it will be isothermal, right? So where I am having the meaning of this average condensate film temperature, there is no point to consider average condensate film temperature because temperature is same, okay. But the point is average condensate film temperature, what we are telling, that if you are handling with one component, if the vapor or whatever you are having, let's say if you are dealing with steam, okay, so condensation will occur only at one temperature, one value, okay. In that case, the average condensate film temperature will remain same, right? Whatever would be the condensate temperature. However, still when condensation will be carried out, still 1 or 2 degree difference we observe when you measure the condensate temperature, but that will be very marginal, okay. Average temperature, when you will see, it will similar to the condensate temperature in terms of pure component, okay, or one component, that may be steam or so, like that. However, when I consider the mixture of vapor, okay, if I'm having, let's say, hydrocarbon mixture, okay, in vapor form, okay, in which different components will be available and each component will have different condensate temperature, okay, because condensate temperature, if you consider, it is basically, it will depend on the dew point, okay. Each component has different dew point, okay. In that case, you will observe variation in temperature in condensation site as well, okay, along with the coolant side. I hope you are getting my point, okay. So in that case, we will consider average condensate film temperature, and that average, and further the average of condensing temperature and tube wall temperature, okay. So here you need to consider two averages. One is for condensation site, and second, the average of condensation site average temperature and tube wall temperature, okay. So based on that, you can find out the average temperature at which you will collect the physical properties. How you will collect the physical property, as we have already discussed in shell and tube heat exchanger. Method is not different, but you need to consider the right value of the temperature, okay. So in that way, you can consider this in that way you can collect the physical properties. And once I'm having the physical property, we can proceed for heat transfer coefficient calculation. As I'm having 4 different type of situation, we will calculate the heat transfer coefficient of all 4 types. The first is condensation outside the horizontal tube. It means you have uh, what we can say, the condensate orientation is horizontal, and condensation will occur in horizontal tube outside. It means shell side condensation we are considering, okay, in horizontally placed condenser, right. So how we will consider that? If you see here, I am having a particular expression which gives which is the empirical correlation for heat transfer coefficient in condensation, okay. So if you see, this is the expression HC1 equal to 0.95 KL, and the other properties, uh, and it will have the power 1 by 3. Okay, so this is the empirical correlation given by Nusselt. Okay, and this is condensation over the tubes, and if you see here, I am having HC1. Okay, HC1 means this is only for one tube. Okay, if condensation you are considering over one tube, then only this expression will be valid. Okay, so it is HC1, and how we will consider that for condensation in shell side, because if you can see the condensation in shell side, we have complete bundle, tube bundles are there, and in between the tubes, in between space in tube, or we can say bundle in shell side, the condensation proceeds. Okay, so this expression is valid only for one tube. Okay, so if you see this HC1 condensation film coefficient for single tube, and single tube means what? If I have the bundle, right? If I have the bundle, the vapor enters in the shell side, okay, and this single tube will be the topmost tube where the condensation will occur firstly. Okay, from where the condensation will start. So this single tube we are considering the topmost tube in the bundle. Okay, so that you can consider. How to consider the complete bundle, that we will discuss. Okay, so here I am having the KL, that is condensate thermal conductivity. The different properties are there which you can see. The uh, uh, that you can see, these are not difficult to understand. Okay, the major point is this capital gamma. I don't know what it is called, but as far as I remember, this is capital gamma. Yes. Now, if I consider this particular parameter, capital gamma, this is called as tube loading, the condensate flow rate, condensate flow per unit length of the tube. Okay, so this is basically condensate flow per unit length of the tube. So it will depend on the flow at which you are getting condensate, which is usually known, and that is kg per meter second. Okay, so in that way you need to consider this capital gamma, and we can have HC1. Okay, now this HC1 is only for the topmost tube. How it will be, it will work for the complete bundle. Okay, so let's see that how it will work. So when I'm having this condensation, okay, this is the bundle. Okay, in that way you whatever liquid is available, whatever condensate will be there, it will, sorry, it will cross this rows. Okay, so these tube rows it will cross. Okay, so as we proceed from top to bottom, whatever condensate is collected from the top, it will move down because of the gravity, right? And condensation will further occur over the bottom tubes. It's not like it will occur only at top of the tube and moves down. uh, the condensation will occur in all tubes, but as condensation will be formed, it will keep on moving towards bottom. Okay, so as you proceed towards bottom, the film thickness of condensate which is available over the tube, that thickness will keep on increasing, as you can observe over here. So if I consider HC1, which is for this particular tube, as we move down, the HC value will keep on reducing because of more thickness of the film, and that more thickness will create more resistance. So lesser heat transfer coefficient you will observe. Okay. So this is the ideal case. And when we consider the actual condition, it will be like this: some hazy type of or some wavy type of film thickness you could have. But of course it will happen, like when we move down, the thickness will keep on increasing, either generally not uniformly, it is not non-uniform, but thickness of the condensate film will increase, that is for sure. So in a bank of tubes, the condensate from upper rows of the tube will add to that condensing on lower tube. Okay. So as proceed down, the condensate will keep on what we can say, join the condensate which is available in lower tubes. Okay. In that case, if there are NR tubes in the vertical rows, okay, NR tube means this, all these tube rows, as we have discussed NCV and NWV in Bell's method. In the similar line, I am having this NR. This is the tubes in the vertical row, and the condensate is assumed to flow smoothly from row to row. And if the flow is laminar, then we can find out mean heat transfer coefficient by considering some correction factor in HC1. Okay, so now I am having HCNR. Whatever HC1 we obtain, that we can multiply by this NR power minus 1 by 4. NR is number of tube rows in the, what we can see, in the bundle. And NR, if you consider, NR is the number of vertical tube rows at middle or at the center of the bundle. Okay, so this NR you can calculate, like you have already understood the NCV and NWV calculation, right? NCV, that is whatever space between baffle tips divided by PT prime. Okay, this NR, how you can calculate that? It will be dB by PT dash. Okay, that would be dB by PT dash, because this is at the center. I hope you are getting my point. Okay, so NR you can calculate power minus 1 by 4 if the average heat transfer coefficient of the bundle will be reduced by this factor. However, when we consider the commercial exchanger, okay, commercial heat exchangers, the Kern suggests that instead of 1 by 4, it should be 1 by 6. It is further what we can say, uh, it it will be slightly higher, because 1 by 6 would be lesser than 1 by 4, but it is because of minus sign. So commercial exchanger, we could experience a bit more heat transfer coefficient than this. So instead of 1 by 4, we will consider 1 by 6. So that you can see over here, minus 1 by 6.95, or the whole expression will remain same. Here I am having NR prime, another parameter I am having, not NR. NR would be dB by PT. Okay, now I am having NR prime. Okay, NR prime will be what? Like, if I'm having, this is the cross-sectional view of the bundle. If you consider NR would be this much: 1, 2, 3, 4, 5, 6, 7, 8. NR is 8 over here. That is dB by PT. PT prime should come over here. Please make a correction. Okay, dB by PT prime. So this NR you can consider at the middle. However, NR prime is what? NR prime is like when you are moving from here to here, okay, and here to here. You will have reduced value of this vertical tube rows. Okay, so whatever NR you will obtain, okay, and whatever NR you will obtain from at this side, NR would be, because of lesser value of NR, the expected thickness of the film would be less in this case in comparison to center. Okay, so as we move from this side towards this side, or I hope you are getting what I am trying to emphasize. Okay, from this side to this side, or from this side to this side, sorry. Okay, this because of that you can understand, I guess, huh? From this side to this side, the uh, vertical tube rows will keep on reducing, and so the thickness of condensate film will keep on reducing. It means whatever heat transfer coefficient you will calculate by considering NR, okay, at the center, it will give you minimum heat transfer coefficient, because film thickness would be maximum over here. Okay, so instead of considering NR, we will consider NR prime, which is 2/3 of NR. Okay, NR prime will be 2/3 of NR. So you need to consider the average value considering the bundle. Okay, because at the center thickness would be maximum. At the this side, left side or right side, thickness would be minimum. So you need to consider average thickness, and that we can consider by considering average tube rows, and that would be NR prime, which is 2/3 of NR. I hope you are getting my point. So in that way you can consider this HCB. This is for bundle now. Okay, if you remember, if you see, this is HCNR. Okay, that is at the center only. Okay, but here I am having this HCB for the bundle. Okay, baki, otherwise you can have this capital gamma H, that is condensate flow by L into NT, that is that you can calculate, and other parameters you already aware. So this is the heat transfer coefficient for condensation in shell side over horizontal tubes. Okay, so in this way you can calculate the heat transfer coefficient. Tube side calculation will remain same. Okay, now I am having condensation outside and inside vertical tube. Okay, so vertical tube rows, vertical tubes, we are considering vertical orientation of condenser, and we are considering outside as well as inside both. Okay, okay. So here I am having a heat transfer coefficient of vertical tubes, okay, outside and inside. So this is HCV, and this is the expression, okay, empirical correlation for Reynolds number less than equal to 30, and this capital gamma V vertical tube loading, that condensate rate per unit tube perimeter. Okay, if you consider the horizontal, it was per unit length. Okay, now it is per vertical, in the vertical tube loading per unit tube periphery. Okay, so in that case you can consider this, and this is for single tube. For tube bundle you need to consider this tube loading differently, like here I am having WC by NT pi D naught or WC by NT pi DI. So this DI and D naught will depend on where side, which side you are considering the condensation to happen, either outside the tube or inside the tube. Okay, or either cell side or tube side, right, like that. Okay, so for tube bundle it is like this. Reynolds number you can calculate by this expression. Okay, however, are having you can calculate Reynolds, you can calculate heat transfer coefficient using this graph also. Okay, and here if you see, this is the Nusselt equation, which is nothing but this equation. Okay, for vertical tubes. Okay, so this is the Nusselt equation, and from 2000 Reynolds number, beyond that it will depend on Prandtl number also, which you can calculate by this expression. And if you see, depending upon the Reynolds number and Prandtl number, you can calculate, you can see the value of this whole expression from this side, y-axis, and this expression value will be equated to y-axis value, and from that you can find out HC. Okay, so beyond, below 2000 also you can use this graph. Okay, it's not like only to only beyond 2000, below 2000 also you can use. Okay, wherever the range is available over here from 100 onwards. Okay, so in this way you can find out the heat transfer coefficient for outside and inside vertical tubes. Okay, outside and inside, how you will choose? Depending upon this gamma V. Okay, as we have discussed in last slide. Now, once I'm having this, the heat transfer coefficient in shell side and tube side of vertical tube, this will be valid for outside vertical tube. However, for inside of the vertical tube, we have another correlation. Okay, so this is given by Boyko and Kruselin. This developed the correlation for condensation in tubes. Okay, so inside the tube, because when the fluid is moving or the condensation proceeds inside the tube, you can understand that when inside condensation will be there, as condensate will form, it will move down. Okay, so it will what we can say, it will join the already available condensate film in the tube. Okay, so it will create additional shear, okay, inside the tube, because the space is that limited. Okay, so in that case, Boyko-Kruselin has given the correlation, and it does not mean that you don't need to use this. Okay, you need to calculate heat transfer coefficient from this graph, as well as from this expression only for inside. Okay, outside condensation, if you are considering, the only from the graph it will work. Okay, inside, for that you need to calculate for both the procedures, for using the graph as well as this correlation. Now this the correlation given by Boyko and Kruselin, it gives the mean coefficient between 2 points at which vapor quality is known. Okay, vapor quality is known, it means, sorry, it means how much vapor is available, that you can quantify. Wherever 2 point is there, you can calculate, between 2 points you can calculate heat transfer coefficient using Boyko and Kruselin. So if I consider condensate, okay, what those points would be inside the tube? One is where vapor is entering, and second is vapor where condensate is exiting. Okay, only these 2 points are available, right? So vapor quality is, we usually denote that by X, is the mass fraction of vapor present. Okay, so how much mass of the vapor is available divided by the complete feed. Okay, so if I consider the ideal case, if complete vapor is entering at saturation condition in condensate, in condenser, it means X should be 1 at the entry. Okay, and if complete condensation is occurring at the exit, X should be 0. No vapor is available, right? Complete vapor is completely condensed. So that is the case. Now, if we consider the vapor quality at 2 points using Boyko-Kruselin correlation, you can have this expression HCBK, that is condensation, and Boyko-Kruselin correlation, equal to HI prime J1 half J1 root over J1 plus root over J2. Okay, by 2 in that, and J1 and J2 will depend on the vapor quality at entry and exit. J you can calculate by this. Okay, so X will depend on the vapor quality at entry and exit. Okay, so entry will be 1, exit would be 0.2. Okay, so in that way you can consider. However, what is this H1 prime? Okay, prime would be the heat transfer coefficient for single phase of total condensate. Okay, the point is H H HI prime, if I am considering, this is the heat transfer coefficient when I am having only condensate. Okay, it means the single phase sensible heat transfer, whatever HI prime you will obtain. Okay, like Reynolds number, sorry, like Nusselt number is a function of Reynolds number and Prandtl number, as we have used before. The same expression you can consider over here because of the single phase and sensible heat transfer, right? So that we can consider, and then J1 and J2, this you can consider as the correction factor. Okay, so when I'm having the that heat transfer coefficient, uh, when the condensate is only flowing through the tube. Okay, condensate filled the tube and was flowing alone, it means only single phase we are considering. And in that case you will use this expression. If you consider this is nothing but the same Nusselt number is a function of Reynolds number and Prandtl number without considering viscosity correction factor. Okay, so that we can neglect. Okay, so in a condenser the inlet stream will normally be saturated vapor and vapor will be totally condensed. If this is the case, as we have discussed before, so J1 will be, you can consider, you can calculate as 1. Expression of J1 we have already seen. In that case X would be 1. Okay, and this is J2 where X would be 0. Okay, so in that way you can calculate. So if you are considering condensation in vertical tube, inside the vertical tube, okay, condensation inside the vertical tube, you need to calculate heat transfer coefficient using this Boyko-Cruzley correlation as well as the graph, and then you can choose the higher value from the both. Okay, so in this way you can calculate the heat transfer coefficient inside and outside the vertical tube. Now fourth case we are considering that condensation in inside horizontal tubes. So when I am considering condensation which is occurring horizontal tube, the heat transfer coefficient at any point along the tube will depend on the flow pattern at that point. Outside horizontal tube, that we have already discussed. Okay, now inside this when I am considering, okay, you have continuous what we can say variation in pattern, okay, from inlet to outlet. Okay, so in condensation the flow will vary from single phase vapor, as you can see over here. And what will happen because of the required temperature at the wall, the condensation will start from the wall and it will make the annular flow. Okay, the liquid will start accumulating at the periphery, inside periphery, and in between the it will remain the vapor will remain will be there. And as further condensation will proceed, the vapor will keep on that annular formation will keep on depleting, and we have large bubble size which we consider as slug flow. Okay, and if bubble size is large enough, it will, because it will move, so it will create what we can say the vibration because of the size of this bubble vibration, where vibration in the tubes. Okay, but baffles and everything is there, so we don't need to worry about that. But if you are considering the single tube and this type of slug flow will be there. Slug flow means large size bubbles, and diameter of that will be equivalent to the diameter of inner inside diameter of the tube. Okay, ID of the tube. Okay, if that is there, so a movement of that large bubble will create vibration in the tubes. Okay, so this is large bubble, and further condensation will give this bubbly flow where bubbles are of a smaller size, and then we have the complete liquid. So in condensation, the flow will vary from single phase vapor at the inlet to single phase liquid at outlet. Okay, with all possible patterns of flow occurring between these points. So from here to here we can have the variation in pattern. And if this is the case, we usually come across with two type of flow when condensation is occurring inside the horizontal tube. And these two type flows are stratified flow and annular flow. If you see, here I am having the stratified flow and this is the annular flow. Okay, stratified flow represents the limiting condition at low condensate and vapor rates. Okay, so if you consider the low condensate rate and low vapor rate, so vapor rate, if it is lesser, it will what we can say, it will not flow very fast. Okay, and it will give the condensate to accumulate at the bottom. Okay, however condensate will also accumulate over here, but in this case condensate flow is less but vapor flow is high, and vapor flow whenever it will be high, it will create that annular formation. Okay, therefore it is called as annular model, and this is the stratified model or stratified flow. Okay, so when we are considering the inside horizontal tube condensation, actually you cannot visualize inside the tube. Okay, that which type of model is forming. Okay, it is stratified flow or annular flow, so you need to calculate the heat transfer coefficient of both the flows and then choose the right one. Okay, so when I'm considering stratified flow, the condensate film coefficient can be calculated by Nusselt equation. Nusselt equation means the first one where we are considering the shell side condensation over the tube. Okay, so that we consider inside the tube. For HC1 I'm talking about only. Okay, not for correction factors and all. Okay, HC1 we have discussed before, where the multiplication is that factor is 0.95 if you recall. Okay, and that we can multiply by 0.8 correction factor, because the film thickness would be lesser at the top inner periphery, and it will be more at bottom of inner periphery. So heat transfer coefficient will be corrected by this factor 0.8. Okay, so the expression would be 0.76 and all. Okay, this is for stratified flow. 0.76 from where it is coming, 0.95 into 0.8. Okay, in that way you can consider the for annular flow. For stratified, sorry, this is for stratified flow, sorry, for stratified flow. However, for annular flow you can use Boyko-Cruzley correlation, and you will calculate the heat transfer coefficient using both the method, both the way, and you need to choose the higher one. Okay, in that way you can calculate the heat transfer coefficient of what we can say horizontal tube when condensation is occurring inside the tube. Okay, yes, so that is about different that is about heat transfer coefficient in different conditions. In all four conditions we have calculated. Other side of that condenser will be normal calculation of heat transfer coefficient, as we have discussed in shell and tube exchanger. Okay, because their sensible heat transfer will occur only. Okay, so that is about the heat transfer coefficient. Other parameter we should consider, like how to find, how to choose this mean temperature difference and all. So just give me 2 minutes break and then I will start this. I will start shortly. So that is about the heat transfer coefficient calculation for condensation in tube side as well as in shell side. And now we will see that how the mean temperature difference will be counted. Okay. Usually in shell and tube heat exchanger we have considered the LMTD for counter current flow, and then we have considered FT correction factor. Okay, so here you can have like you can have mean heat transfer, mean temperature difference in different ways depending upon the condition and what is that condition. If I'm considering pure vapor, let's say steam, if you are considering, which has fixed temperature of condensation, okay, at constant pressure, so that is basically isothermal condition. In that case, isothermal condition will happen in one side, and second side coolant is there, so I am having this sensible heat transfer. Okay, so in that case LMTD you can find out by this. Okay, if I draw the temperature profile, it will be like this. Heat, the saturation side, it will be the constant temperature, condensation temperature. However, for other side it will be change in sensible heat. Okay, so in that case you will have to find out LMTD. Okay, LMTD, and that should be simply calculated by this. Okay, LMTD you can find out. Now, instead of pure vapor, if I am considering mixture of vapor, mixture of component in the vapor, in that case, as I have told you earlier, that you will observe variation in temperature in condensation side. Okay, it won't be isothermal process because each component has different dew point, so it will condense at different temperature. In that case you will find variation in temperature in condensation side as well as in coolant side, both way. So if this is the case, you need to calculate LMTD for counter current flow, and that should be multiplied by FT correction factor. FT correction factor, when you consider, where you need to count that, it counts the temperature cross. Okay, temperature cross is only possible when I'm having uh, like when I'm having variation in both the side in temperature. Okay, if I consider this particular case, uh, because uh, uh, because what is temperature cross? Temperature cross means this temperature should be higher than this. Okay, so if I consider this temperature as well as, sorry, this temperature as well as this temperature, or wherever, in this case temperature cross will never occur because one temperature is isothermal and that too it is at high value. Okay, wherever I am having variation in temperatures in both the side, there I am having the possibility of temperature cross, and there I should consider FT correction factor. So that you should keep in mind. Okay, this is the same thing. So if this is the case, if you are dealing with mixture of component in vapor, then you should calculate LMTD correction factor with uh, FT correction factor. Okay, so in this way you can consider mean temperature difference. Now, when I am considering condensation, so far we have discussed only this part. Okay, condensation is occurring, that is at particular temperature, and second I'm having the coolant. Okay, but apart from this we usually have two more condition. One is de-superheating and second is subcooling. Okay, de-superheating, when I am considering, let's say uh, if you need to bring the if you need to prepare the steam, let's say, it will be prepared in a boiler, right? And if we consider from boiler, steam will be produced, and that steam should be used in a heat exchanger. Okay, so steam should be brought from uh, boiler to heat exchanger, right? I hope you are getting my point. So while movement of this, some heat loss will definitely occur through the duct or through the pipeline. Okay, so in that case, is it very much possible that if you are allowing saturated steam to exit the boiler, it will reach to the exchanger after some condensation. Therefore, to avoid that, we need to provide, we need to uh, prepare the steam at slightly superheated condition. Okay, so that after heat loss through the pipe, it will reach to the saturated condition. Okay, so in that case, if your vapor or steam is available at superheated condition, the up to certain extent I am having de-superheating, then condensation, and after that, if you require the vapor, the condensate should be completely, what we can say, it should be complete condensate, or that should be slightly lesser temperature. If you need to store or something at a particular temperature, then I'm having subcooling as well. Okay, so if this is the case, usually in condenser this type of situation occur, that steam enters at superheated condition. Okay, saturation reached in the condenser, and then subcooling is also considered in in the condenser only. Okay, so if all these things are occurring in a condenser, then how we need to count that? Okay, so let's see that if I'm having this de-superheating clubbed with condensation. Okay, so let's see. If I consider de-superheating along with condensation, in that case, if the degree of superheat is large, degree of superheat means uh, this is degree of superheat means Q, whatever heat would be transferred through de-superheating. Okay, so if degree of superheat is large, it is necessary to divide the temperature profile into sections and determine mean temperature difference and heat transfer coefficient separately for each case. What does it mean? If sufficient de-superheating we are considering, what is the meaning of that sufficient, that we will discuss. Okay, so if whatever is what we can say, superheat, degree of superheat is large, then for this case and for this case, heat transfer coefficient will be calculated differently, because in this case the mean temperature difference would be based on this and this. Okay, so that would be LMTD into FT. In this case, it would be LMTD only. So heat transfer coefficient you will find different for this case and different for this case, and then you need to consider weighted correction, sorry, weighted heat transfer coefficient weighted on duty, right? So in that way you can consider heat transfer coefficient and mean temperature difference will be calculated separately, and then you can find out the area. Okay, by making these weighted with respect to heat load. Okay, now if amount of superheat is less, amount of superheat is less means 25% or less than that. And if I consider this case, in this case, if it is more than 25%, okay, the Q value of the superheating. Okay, so if superheating is less than 25% of latent heat of load, the meaning is this is the latent heat load, and if this load is 25% or less than this load, in that case The sensible heat load of de-superheating can be clubbed with latent heat load. It means in that case you will consider from here to here. So, up to here, sorry, up to here. Okay, from here to here you need to consider the heat load, and then you need to design the condenser based on the condenser design, not the de-superheating, right? So if this is the case, total heat transfer area required can be calculated by mean temperature difference based on saturation temperature, not superheat condition, and estimated condensate film heat transfer coefficient. Okay, so in that way the condenser will be designed based on condensation only, not de-superheating. Okay, in that way you can consider. Similarly, if I am having subcooling, you understand, that is to reduce the temperature of condensate. Okay, so little amount of subcooling of condensate will usually be required to operate the condensate pump or to cool product for storage. If you need to bring the what we can say, the condensate at storage temperature, that should be well below than the condensation temperature. Okay, so condensation so that temperature at storage condition can be brought by subcooling only. Okay, so where the amount of subcooling is large, again the same thing, more than 25% of duty of condenser or latent heat of the condenser. If amount of subcooling is large, it is more efficient to subcool in a separate exchanger. Okay, so in that case you need to consider the condensation in different exchanger and subcooling in different exchanger. Okay, a small amount of subcooling can be obtained in the condenser by controlling the liquid level so that some part of the tube bundle is merged in the condensate. Okay, so certain amount of subcooling we required by making this dam baffle. So this is the vertical cut, and this type of structure we provide, and condensate up to this much height. Okay, up to this much condensate will remain there. Okay, otherwise we usually prepared a V notch over here. Okay, from this condensate should exit, but we are not doing that over here. If we required a little amount of subcooling, that is less than 25% of latent heat. Okay, in that case uh, uh, condensate which is available above this, that will only be able to flow out. Okay, and the this type of case, when we are considering, it means some part of the bundle is merged in the condensate, that you can see over here. Okay, some part of the bundle will be merged in the condensate, mm, to ensure that like if you consider the movement of condensate, it should pass through pump, right? And pump should have the complete liquid, not the mixture, to ensure that some of the tube bundle should always be merged in the liquid. Okay, so this we do for horizontal case, and this we consider for vertical case. Okay, so liquid head should always be there, condensate head as the form of liquid, right? So in that case you consider the subcooling, and in sub cooled region, heat transfer coefficient is estimated considering natural convection, and that should be around 200 watt per meter square. So that value you can consider as it is. Otherwise for condensation you need to find out heat transfer coefficient based on usual expression which we have discussed in today's class. Okay, so in this way you can account de-superheating as well as subcooling both in the condenser. Okay, so in that way you can design the condenser with respect to heat transfer coefficient. Okay, now how we will calculate the pressure drop in the condensers? The pressure drop in the condenser pressure drop on condensing side is difficult to predict as two phases are present and vapor mass velocity is changing throughout the condenser. So what happens that initially vapor is there, so that velocity will be different, and as the uh, what we can say, as the condensation will proceed, the vapor amount will reduce, which has different velocity than it is at the entry. So in that way we can consider the different, how we observe the difference in velocity, because it is mass flow rate, you that will remain same. Okay, but when we consider the vapor mass velocity, because of the that formation of condensate, the density of the mixture changes, and so we observe the uh, velocity change. Okay, however, if we consider the vapor mass velocity, because condensation is formed, so vapor amount will keep on reducing, which will reduce the velocity. Okay, density of the vapor will remain same, but the velocity will differ because of the mass change in mass. Okay, in that way you can consider. So when I'm considering this, what happens that we will calculate pressure drop of condensation side. We will calculate pressure drop of condensation side considering single phase flow. Okay, considering single phase flow, and then that would be corrected by some correction factor. Okay, because it is for single phase flow and that cannot be used for vapor. Okay, so that should be reduced then the vapor, uh, because of the continuous uh, formation of the condensate. In that case, whatever pressure drop you will calculate for single phase flow, you need to consider just half of that as the pressure drop in condensation side. Okay, so this is the case that pressure drop you need to consider for single phase, and just half of that you will consider a pressure drop in condensation side. Okay, another side sensible heat is there, so that calculation will be done normally. Okay, so this is for total condensation, and that we consider like this, and this design is preferably for total condensation, not for partial condensation. Okay, so in that way you can design the condenser depending upon different condition. Just 1 minute, please. Hello. So in that way you can design the condenser depending upon the orientation as well as condensation side. Okay, so that is about the condenser. That is all about the condenser, and I will start another topic from the next class, and I will give one problem on this condenser also. Okay, but that you can do after the shell and tube heat exchanger design. Okay, so we will start the next topic from the next class. I'm really I appreciate your patience. So thank you everyone. If you have any observation, please let me know.
Ma'am.
Okay, thank you, Beta. Thank you.
When can we get these slides on mail?
Sorry?
These slides you have shown in the class, can we get that material?
Yes, yes, I will show. I will share. I will share.
Okay, ma'am.
Okay, but
Previously
actually,
written your
I
message.
will.
Yes, ma'am.
Yes, tell me.
Previously, I had asked you, but got no reply. So, just
When
to
you have
confirm.
asked, sorry?
Mm, about
Today?
2 weeks ago.
Oh, I didn't remember that. Okay, I will share. I will share. No problem. But that will be like for shell and tube heat exchanger, because different hyperlinks are there. Okay, but I will share those PPT form. You can go, you can see the like respective slides. Like if I consider the properties, the property has one PPT of properties there, so that I hyperlinked. Okay, but I will share the all the PPT, and you can see by the name you can figure out that which hyperlink you should open. Okay, so that I
Sure,
will
ma'am.
do. Uh-huh. Thank you, thank you,
Thank you, ma'am.
thank you.